So in this part, we'll talk about the MAC. So remember, in the previous part it was all phi, physical layer. We talked about how these carriers and things are allocated, but we haven't talked really about the packets. So this part is all about access, media access control. So we'll talk about the key features of the MAC, the quality of service classes, the ARQ, which is basically retransmissions, and hybrid ARQ. In case of errors, we do retransmission. What is the protocol? What are the protocol structures? The payload, header suppression, all the different headers, scheduling and link adaptation. So this is all about MAC protocols in WiMAX. So the key features of the WiMAX MAC is that it is very flexible and extensible. So the same MAC can be used for all current and future files. So remember, we had 16, 16A, 16D, 16E, 16M. Those are different versions of the IEEE 16 standards. So all these standards have something new, but mostly in phi. The MAC has been stable. Actually, it doesn't say on this slide, but the MAC really came from cable modem. So if you have a cable modem at home, it uses a media access control. That is what WiMAX just borrowed from cable companies. And so that is MAC. So the same MAC. So it's very flexible, modular, several optional feature and negotiations. Then multiple topologies. It allows point-to-point, point-to-multi-point, mesh, and so on and so forth. Multiple access antenna technologies. So it allows adaptive antennas and MIMOs. Multiple protocol payloads. It allows ATM networks, ATM as well as IP. Anybody knows what is ATM? Ever heard of ATM networks? What does it remind you of? Huh? Yeah, so the ATM networks were designed for the phone company. That's good. There is any other thing comes to your mind? Basically, they used to have small cells, fixed size cell, 53 byte cells. So anyway, so this can be used with that and packets and so on and so forth, with and without header suppression. So generally what happens is IP headers are big, 40 bytes, and on wireless networks we can't really send all 40 bytes, so we compress them to 3 or 4 bytes. So we can use that method here. Flexible retransmission policies. So we have HARQ and ARQ, which we'll talk about. It supports both TDD and FDD. It supports, what is TDD and FDD? Do you still remember? Yeah, good. Good. Variety of subscribers, several per subscriber and per connection parameters, integrated quality of service. So I mean, basically quality of service is already we talked about, it has it, and it is very secure. So basically, this is centrally controlled system. So there is a base station which controls everything. So base station tells who can speak when. And so what does base station do? It controls the entire system. It controls the frame size. It controls the scheduling. It controls who can get into the network, admission control. It controls the quality of service. It does the ranging, which means finds out who should transmit how much power. It does the clock synchronization, power control, and handoff. So these are the things that the base station does. What the subscriber station does? It finds the base station. It acquires the physical layer. So basically it tries to find out where the right frequency and the time is. It obtains the MAC parameters from the base station and generates the bandwidth request, makes the local scheduling decisions. So there are 2 scheduling decisions. The subscriber station has 5 traffic going. It has a phone call going. It has some web access going at the same time, and it's, some VoIP going, and so on and so forth. So all these different traffic applications need different quality of service. Some need high throughput, some need low delay, and so on and so forth. So it has to put them in multiple queues and decide which packet will go first. Right? So that is the subscriber station job. But the subscriber asks the base station that please, I need to send 1500 bytes and some of them are so critical and this much or this is so critical. So it tells all that to the base station, and then base station tells that okay, you have 500 bytes to send at this time. So the base station decides total bandwidth given to a station and the time, and then the station has to decide on its own which of its own traffic will go first. So there are two schedulers. Local schedulers follow the transmission and reception schedule from the base station, perform initial ranging, maintain the ranging and power control. Mobile station also does mobility management, handoff and power conversion. So now we kind of interchangeably use MS and SS, but there is a difference. SS is a subscriber station which could be a home, and MS is a mobile station which is a subscriber station but also mobile, which could be a phone, for example, or a laptop is a mobile station. But we won't really distinguish that way because, I mean, you know, everything today is mobile, so almost all subscriber stations are mobile, and there is very little we will talk about where things are not mobile. So every SS is an MS and MS is an SS already. So anyway, but MS have to worry about mobility management, they have to worry about handoff. What is handoff?
Moving between cells, like
yeah, when you switch a base station. And the power conservation, and then it has to go to sleep because mobile station generally has running on battery. It is running on battery, so it has to worry about that. All right. So framing and duplexing. So now each frame consists of many bursts. We have already seen that. Each burst has many PDUs. So we talk about PDU. PDU is the protocol data unit, and MPDU is the MAC protocol data unit, right? So each layer, say application layer is called APDU, because application protocol data unit. Transport layer is called TPDU. Network layer is called NPDU, and the MAC layer is called MPDU. So that is the packet at the MAC layer. So we can put multiple packet in one burst. Okay. And then the burst profile basically tells us what modulation type, FEC, preamble, etc., and how much guard time, etc., is required. That is all in the burst profile. And rather than specifying everything in detail, we generally give them a code that, okay, you use the profile number 13, and that is called downlink interval usage code. So that code, DIUC, indicates what burst profile you have to use. All right. So that is simply, that bit is short number of bits that can be used to tell you all of this detailed information. Because there is a whole table that you have in the beginning, which tells you all the codes, and then every time will tell you, okay, send the burst at this time, and using the code number 12. So that is DIUC. Channel descriptor, downlink channel descriptor, DCD. This describes the downlink PHY, and it is broadcast periodically by the base station, and in that is like a beacon, and it indicates the frame duration and defines all these codes. Okay, so DCD, this defines the downlink. Basically it is like a beacon which tells these are the codes I am using here, and this is my frame duration, and these are the other parameters. Whatever is constant over multiple frames, that is broadcast every few frames. Uplink usage code is similarly to DIUC is uplink. So there are different codes for uplink profiles, and so that is UIUC. And the uplink channel descriptor is similarly different than the downlink, where all the parameters of the uplink are specified. Okay. The maps are basically staggered. So when you get a frame, so this is, let's say, one frame, uplink and the downlink. sorry, the downlink and the uplink. So in the downlink, first thing you get is a DL map. And the DL map tells you the map of the rest of the downlink subframe. Then there is a gap and there is an uplink frame, but the UL map may describe the frame next one, not this one. So when you get a map, it tells you that, okay, in the frame after this, you are allowed to transmit at this time. So that gives some time for the mobile station to get ready. All right. While receiving, they don't give you time. For receiving, you get the map and you receive. Okay. But for transmission, you may get an extra time. And this is actually basically may be broadcast one frame ahead. So it is not necessary. They could be just broadcasting here. And all that will be described in the DCD and UCD as to what they are doing. But anyway, so the thing is that the UL map may or may not correspond to the same frame. Is that point clear? It's like this. When you raise a finger and say, I want to speak, I may not just tell you that, okay, now you can speak. I may give you some time and say, okay, all right, after this you can speak now. So that's how it is, that the uplink map tells the stations when they can speak, but that speaking opportunity is in the next frame. So this is frame number 1. Each frame consists of the down and up, down and up, down and up, and down and up. Okay? Is that clear? How does the map point to? If it's not clear, please ask. Not clear? Okay. All right. Now each station sets up many connections. And so service flow is a higher layer flow. So for example, Skype might set up a flow. Actually, Skype might set up multiple flows, depending on, it might be having a screen sharing going, it might have a voice going, it might have a data going, and so on and so forth. So each higher layer flow is a service flow. Each service flow has is a connection, and so you could have up to 65,000 connections. And in addition, there are some connections which every station has anyway. So there is a connection for initial ranging, on which they talk about the power levels and so on and so forth. There is a connection for basic management. There is a connection for basic CID, which is basically always there. And so these are always there. In fact, all of these are always there actually. But that is the first one. Then there is primary management, secondary management, multicast polling, and so on and so forth. So there are many connections which are there even without any bytes being sent for the user. But when a user comes along and they might have many service flows, those are additional connections. So everything is connection oriented on this one. So whenever a packet goes, it has a connection ID in it. It says, well, this packet belongs to connection number such and such. And connection ID is 16-bit long. Quality of service, there are 5 quality of service, and they are called UGS, ERTPS, RTPS, NRTPS, and BE, best effort. So what is UGS? UGS is unsolicited grant service. That means that you don't have to ask for it. You ask for it actually in the beginning, but not every frame. So if you want UGS, when you set up this new connection, at that time you say, I need 3 kilobits per second for this voice connection, fixed. It doesn't go down, doesn't go up. So that's why it's called constant bit rate, CBR. It's a constant bit rate connection, and you get that in every frame. You will get an allocation, not every frame. You will, in certain frames, you will get an allocation for those connections, because those are already, the base station knows that you need to send that many bytes every so many millisecond, and so it will allocate you accordingly. So that is UGS. Second set of those which are time critical, actually not time critical, this one is for voice. Time critical voice uses ERTPS, So if it is silent suppressed voice, then it uses ERTPS, which is very similar to UGS, but it is on-off. On-off in the sense that you say, well, I am using 3 kilobit voice, so I need it all the time, but only when I am speaking. When I shut up, then I don't need it. All right? So this is a silence suppression. So otherwise, if it is not silence suppressed, then you are getting the bits all the time, but you are not speaking. Right? Those go waste. So therefore, they invented this new class which is fixed, which is almost like CBR, constant bit rate, but it is on-off. So when you want to go off, you just say, I'm going to go off, and then you tell when you want to come up, and you say, well, I want to up now, come up, and then, you know, once you come up, they know exactly how much you need. That is ERTPS. Then there is a real-time polling service where you have real-time, means time-critical thing like a video, streaming video, or video conferencing, more like video conferencing. So you need a particular delay jitter, particular throughput, and for that you use real-time polling service. And it is called real-time polling service because the base station asks you what you need, and then so they are polling you, and then you respond to that and say, well, I need so much. Non-real-time polling service is NRTPS, which is used for when you need some guarantees of throughput but not delay, and so that is NRTPS. And then best effort is when you don't need any guarantees, and so that is best effort, which is the normal IP traffic. And there are 5 classes. All of these classes came actually from the cable modem companies, and all the cable modem companies got it from ATM. So if you knew about ATM, then these all will sound very familiar. The only thing which was added in WiMAX actually, which was not there before, is ERTPS, the silent suppressed voice. Otherwise, the other 4 were there in ATM. From there they went to cable modem standard. From there they went to WiMAX. Yeah, question?
So the real and non-real time, what is the difference there?
Yeah. So there are 2 kinds of traffic. Okay. So there are two kinds of videos. One is real-time video and non-real-time video. So real-time video is video conferencing. If we are having video conferencing, if I raise my hand like this, and if you don't get my raised hands like this, you know, for a minute, you will be concerned, right? Non-real-time video is watching a movie. So watching a movie, if everything is delayed by 1 minute, you won't miss anything, right? So, but you need some guarantees for both videos because they are very high bandwidth, high throughput, and therefore, so if you are doing a non-real-time video, then you will use NRTPS. If you are using real-time video, other example of real-time video is what? Can you think of another one where you need real-time? If things are delayed by even a second, you would be kind of missing something. Can't think of anybody plays games? So if you have an internet game and you shot somebody and they didn't see your shot for 1 second or 2 seconds, they shoot you, that won't be very good, that you thought they were dead but they were not dead. You know, kind of thing, right? So there are real-time games. Right? So that's an example of real-time, where time is very critical. All right, any other question about the quality of service classes? All right, so we have 5 classes, and then basically we have, now we are moving on to a totally different topic, and that is what do we do if something doesn't get right through. So if there's an error in the packet, then we have to do retransmission, and that is called ARQ. ARQ stands for Automatic Request, Automatic retransmission request. So basically, first of all, let's go through this, how we send the packets. So this is the MAC layer, it gets some SDU. SDU is the service data unit. So the higher layers give it the packets and we call them SDU. So SDU could be IP datagram, for example. This is the network layer thing. So network layer gives some things to the MAC layer. We call them SDUs. MSDU to be exact. MSDU is the MAC SDU. We break them into what we call blocks. And each block is what is can be retransmitted. So when something goes wrong, we don't retransmit the whole SDU. We just retransmit a block. So each block is called ARQ block. So this SDU became 3 ARQ block, this SDU became 2 ARQ block, this SDU became 3 ARQ blocks. Then some of these blocks are put into a PDU. So this is a MAC PDU 1, this is a MAC PDU 2, this is a MAC PDU. In this MAC PDU we have 2 ARQ blocks. In this MAC PDU we have 4 ARQ blocks. In this one we have 2. Alright? And then we haven't shown you further, these go into a burst. So there might be a burst in which we might have 2 MAC PDU or 5 MAC PDU, depending upon how much time we are given. But anyway, notice that this SDU is 3 and 4 and this whole thing is here. So we put a header in the front of it, which would be basically the PDU header. This 6 and 7 is only part of the SDU. So we put a fragmentation subheader here. So we tell, so that when the receiver gets this PDU, they know that this is not the whole thing. This is only a fragment of the whole thing, and it has to combine it with the previous one to make the whole SDU. So basically, these SDUs are coming to the transmitter MAC. It breaks them into the blocks, then puts them into PDUs and sends them off. At the other end, the opposite happens. The MAC PDUs become these blocks and they become SDUs. So exactly the same size SDUs are given to the receiving IP. Right? And so anyway, so the ARQ is done at the block level. If something goes wrong in this block, the acknowledgement will be sent that we did not receive the block number I, and block number I will be resent. So there are 3 concepts on this slide. First is that the ARQ block is not the same as the PDU. Each PDU consists of multiple ARQ blocks. Alright. Second concept is subheaders. So there are 2 kinds of subheader. There is a packet subheader which is shown by blue. Or PDU subheader, basically that is PSH. That is the PDU subheader that tells you the beginning of a PDU. And there is the FSH fragment subheader which is put in front of a set of blocks which do not form a complete packet because they are continuation of the previous PDU. Yeah.
So when that arrow is pointing to a PSH, that's part of the fragment, isn't it?
No, this is a whole packet H2, I plus 2. Yeah, I think you are right. This should be blue and this should be yellow. Let's see if I can make it correct. It's too much work right now. But yeah, I'm going to continue. So this should be the PSH and this would be FSH, PSH, PSH, FSH. Yeah.
Are these headers inside the block or outside the block? I mean those FSH and PSH.
Yeah, so let's see, that's a good question. I will have to check that. I'm not sure. My, what you call the common sense is that this should be part of the block, because it's not worth putting them separate, and they're just 2 bytes long compared to the block which is multiple byte long. Alright, that is ARQ. So that's all we're going to say about ARQ. Now we're going to move to HARQ. So HARQ is the physical layer ARQ. So ARQ is at the MAC layer, where we do this retransmission of the packets. But we could also get some help from the physical layer. That's why it is called hybrid. So hybrid is HARQ, hybrid ARQ, which uses both physical and the MAC layer. So it uses the help of the physical layer in the sense that what it does is when you have a block missing, or you have a block in error, then we send another copy of the same block but with some different coding. So the file layer has changed, and it is possible for the file layer to now get those bits that were in error correctly by combining these 2 codes. So there is something done at the physical layer to re-decode better using these 2 transmission. So that is called HARQ. So hybrid. So basically ARQ is a pure MAC function. HARQ is combined MAC and file layer function, in which the second copy may use a coding such that it allows the physical layer to reconstruct the data better. Okay? And so the receiver tries to decode using both first and the second subpackets, and the process continues until the 4th subpacket. So this is done 4 times. If you got it in the second time, then fine. If not, 3rd time we send another copy. 4th time we send another copy, and after that we give up on the HARQ. Okay? So we know ARQ and HARQ. Then we move on to the protocol, other protocol layers. So there is a physical layer, there is a security sublayer, there is a MAC sublayer, and then there is a service specific convergence sublayer. So this is called SSCS, or CS to be short. This is the common part sublayer, or CPS. This is security and physical layer. The MAC consists of all these 3 parts. So what is done in the convergence sublayer? It says service specific, and that indicates basically what it is that MAC offers many different services, and so this is for each service there is something has to be done before we do the common thing. So this is service specific. So it classifies the SDU based upon the MAC address, VLANs, priorities, and so on and so forth. So it decides whether it is a VoIP or whatever it is. Assigns the service flow ID, then it puts it on the right connection, because there is no connection before that. IP does not have a connection, so when the IP gets the packet, it doesn't say what connection ID it is. So the MAC finds the ID and puts that, and it can also do the header suppression. So if it is an IP packet, then IP header can be compressed in a particular way, and so that is done in this service specific part. In the common part, only the fragmentation, reassembly, and the ARQ, etc. is done in the common part. So in the common part, fragmentation and assembly of large SDUs, and packing and unpacking of several small MAC SDUs. What is packing? When we put multiple PDUs into multiple SDUs into one PDU, that is called packing. Okay? When we put one SDU into multiple PDU, that is called fragmentation. So the fragmentation is opposite of packing in some sense, right? If you have lots of small SDUs, you pack them. If you have a big SDU, you fragment it. Okay? So all that fragmentation and packing is done in the common part. In the service specific part, we do things which basically are specific to whatever application you are using, and the network layer and so on and so forth, and that includes the packet header suppression. And the common part continues actually. The common part also has QoS, scheduling, bandwidth request, and ARQ. So we talk about, we have actually another slide coming up on scheduling, but basically every station has to request every frame how many bytes they need. So that is called bandwidth request, and then they are told in the UL map the opportunities for transmission, and so that is all scheduling. So let's first talk about the packet header suppression. Now, so the header, and this is we are talking about the IP TCP header. Everything basically, so the first part of the packet that is received, or SDU that is received, will have many bytes which are always same, because the headers don't change that much in so you get one packet from IP, and then you get the second packet from IP. They are all having they're going to the same destination. They are probably have the same all other header fields that are very similar, except few bytes might have changed. For example, sequence number might have changed. The flow acknowledge might have changed, but everything else is fixed, and therefore it is not worth sending all of that all over again. So there are fixed bytes, and there is a mask. So the mask says which bytes are fixed and which bytes are not fixed. So basically, we could send the header once. We could send the header once and send you a mask saying that, look, here is the header for this packet, but the byte number 1, 5, 7, 13, and 14 will not change. All right, I will send you the rest. So this is a mask, and then index which rule. So what they do is they have many different rules, and so based upon that, if I told you that here is the incremental data and apply rule number 13, rule number 13 says that, well, add these bits to this particular byte and you get the new byte, so that is the rule. So which rule? So using those three things, we can construct the whole header at the other end. PHS verify, compare before removing. So basically, we could also send a verifying request where here is our header, and then you see that your rules, etc., and mask, etc., are all correct. Okay. So with this method, actually, the 40-byte header can become 3 bytes. So here is an example. Sender gets this header. This is the mask 101010, and this is after applying the mask and the rule, we get these 2 bytes are the only one that have to be changed, sent. B and D, A, C, and E are fixed. So we send B and D on the air. At the other end, we put B and D at the right place, and we take rest from the table, and we get the whole table again, whole thing again. Is that clear as to how and what is done? So we do have to send the whole header once, right? The next time when we have the header, we just see what is the changed, and we just send the mask and the values. Okay. Now in terms of the headers, each PDU has a header, then it has a payload, it has its indication whether there is a CRC or not, and then it is encryption key, length, the common identifier, the connection identifier, and the header checksum. So this whole thing is header. So this whole thing is 6 bytes. So each PDU has a 6 byte header. This is what we called before PHS, not PHS, we called it PSH. PSH was PDU subheader. So the header type could be generic or standalone. You don't know the difference. Encryption control, 1B tells you whether there is encryption or not. Payload type tells you what kind of payload it is, and there might be different kinds of things anyway. CRC indicator, whether there is a CRC with this, and CRC is optional. Reason CRC is optional here is because the whole burst has a CRC. So we don't need to have CRC in every PDU. Then there is security stuff, length, connection identifier, header checksum. So this is a checksum for this whole thing. So if there is any error here, the checksum will not match in the header. The payload types are that this is a packing, fragmentation, ARQ, and so on and so forth, different kinds of payload, right? That includes that this is with ARQ or without ARQ, and so on and so forth. So that's payload type. Then there is a bandwidth request header. So this is a PDU. This is not a PDU. This is basically, if you want to send a request, then you will formulate a 6 bytes total. This whole thing is 6 bytes. There is no payload here. And this will have the header type, the encryption control, and then it will say which kind of request it is, incremental or aggregate. Incremental means I need 6 more bytes than over what I told you before. Aggregate means total I need is 200 bytes right now. So forget the old one. So this is incremental or aggregate, and how many bytes I need, what connection ID it is for, and then the checksum. There are other headers such as fragmentation subheader. So there is a fragmentation subheader, that is FSH. It has 2 bits for fragmentation control, 3 bits for the sequence number, and 3 bits are reserved. So what is fragmentation control? Fragmentation control means no fragmentation, last fragment, first fragment, middle fragment. So that will indicate whether it continues or this is just the beginning or the end. And then the block sequence number is that number we saw, IEEE +1, etc., etc. Fragment sequence number is mod 8 or mod 2048. So there is a fragment sequence number and there is a block sequence number. So if you are doing ARQ, then you put the block sequence number. If you are not doing ARQ, then you do the fragment sequence number, in which case there is no retransmission, and you don't have to have the blocks fixed size. Here it is fixed size blocks, so we put the block sequence number. And then there is extended fragment subheader, which is used under some other conditions. So anyway, so there are basically the key idea here is not to remember all these different sizes here, but to remember that there are many different kinds of headers and subheaders. The main thing is this one 6 bytes, but then there are 2 bytes subheaders, 2 bytes. This is actually only 1 byte. This is 2 bytes. This is 2 bytes, and this is 2 bytes. So, so depending upon yeah, I don't know what is 1 byte thing, because generally all the subheaders that I knew were 2 bytes. So there might be something else missing here which I haven't put. And so, so basically there are subheaders which are put in front of the fragments and ARQ blocks. All right. In case of packing, we put the packing subheader. So fixed length SDUs. If it is like ATM cell or something, then all these things are fixed length, and therefore we can just put a packing subheader. If it is variable length SDU, then we have to put this 2 byte PSH in front of every SDU. So we know that this SDU, where it begins, where it ends. Then there are other subheaders for grant management, which means making requests. We always have the request, but then there are others such as UGS connections may use this one, UGS grant submanagement. So UGS connections say, well, please poll me now. I need to start sending. Non-UGS connections use some other subheaders, which is basically, it tells you exactly how many bytes we need. So that is number of incremental bytes required. And extended piggyback request. So this is for ERT PS class. In this class, which is like a UGS, but on off, 11 bits are used for incremental request, and then if the first bit is set, then the 4 bits indicate the requested polling size, and the queues build up, SS sets the MSB, and the BS shift the grants earlier. Basically what happens is, because of the silent suppression, the size of the number of the bytes that you have in your queue could be small or large. And if the queue becomes very large, then you set the MSB, and then you say, well, please change the polling size to 16 byte units or 32 byte units. So that indicates the polling size, and once they poll, then you can say how many bytes you have to send. Or you can just send 11 bits and indicate that I need that many more bytes. It's one of the two ways. If you use MSB, then this indicates the polling size, otherwise this indicates the total request. Yeah? Oh, it's time? Okay. All right, we'll continue on this point. We'll repeat this one again, and then